Okay, so we welcome everyone to the IIT Bombay Virtual Commutative Algebra Seminar. We are very happy to have Professor Vijaylaxmi Trivedi from Tata Institute, Mumbai, and she will speak on the Hilbert-Kunz density function. The talk will go for 1 hour. At the end of 1 hour, we will have question answers. During the lecture, you can type your question in the chat box and we will relay it to Professor Trivedi. So the seminar can start now.
Okay, so thanks for the invitation. Am I audible?
Yes.
Yeah. So the first part of my lecture, I'll begin with preliminaries about HK multiplicities. And I'm afraid that many of you must have seen in the previous few talks the definition, but I need to do it just to set the course for my lecture. So the most general way of defining HK multiplicity is that you take a Noetherian local ring of dimension say D, and the ring should have a positive characteristic. Now, given an ideal I, you define a Frobenius power of I as follows. You take the set of generator, choose any set of generators, and raise to the power q. So here q is Pn for all n now, because I don't want to write p to the power n, which should be the correct way of writing, because the notations will look very cumbersome later on. So what you do, you raise those generators to the power q. So and take the ideal generated by that. Other way of looking at it, you consider the Frobenius map from R to R. It's a ring morphism because your ring is of characteristic P. So the nth iterated Frobenius power is given by x goes to x to the power Pn. So you just take the image of that ideal and take the ideal generated by those elements. So you may wonder that the notation does depend on the choice of generator in the first definition, but you can check it is not so. So these are called Frobenius power of the ideal I. Okay. So early 80s, Monsky introduced this invariant given a pair R and I, which he called HK multiplicity of R with respect to I. So you take the length function R mod I to the Frobenius Q. So since in the beginning length of R mod I is finite, this makes sense. It's a finite. It's a finite length. And what you go modulo Q to the power D, where D is the dimension of the ring. So this limit as Q tends to infinity, or power of n tends to infinity, it does exist. That's his theorem. So moreover, it belongs to it's a real number, of course, and greater than or equal to 1. So much before that, actually the Kunz has considered these length functions. So the Kunz was looking at these functions from the point of measuring the regularity of the ring. The Monsky did study in a different context. So what he did, his way of looking was a number theoretic point of view, because he's a number theorist. So he took a tower of number fields and look at the ideal class group and look at how the P part of that ideal class group grows. So this is over, of course, power series you can formulate, but he realized you can completely put this invariant in a algebraic context, and this invariant after that is very popular with commutative algebraist. So now if you look at this invariant, this of course reminds you of the another very well-known invariant, which is Hilbert-Samuel multiplicity. So again, you start with R and I. So here ring need not to have positive characteristic. I'm not going to use that here in the definition. So you take length of R mod I to the power n. So and go modulo n to the power d. So so add d factorial also. This is the notion we have. So this limit also exists. It's in fact, it's a leading coefficient of a polynomial called Hilbert-Samel polynomial. So this makes perfect sense. So on one hand, you have I to the power n, and on the other hand, you have I Frobenius q. So you're taking go modulo the same power, p to the power nd, and here also the same thing you'll be going. So question is, what is the relation between these two invariants? So this was the first observation Monsky made when he introduced. So this EHK-RI is less than or equal to E of R mod Hilbert multiplicity of R at I, and it's greater or equal to maxima 1 and multiplicity mod E factorial. So it's easy to check. This is obvious from the definition because I to the power n is naturally bigger than the ideal I Frobenius q. I to the power pn is naturally bigger ideal than I Frobenius q. So this equality will hold. And for this, what you do, you take a minimal reduction ideal of I. So it's given by, say, system of parameter. And you look at its length function in the sense of Hilbert-Kunz multiplicity. Means you just go modulo those generator raised to the power q. So that itself, if I look at the length this way for the ideal j, then it's by Lecq formula is a Hilbert-Samel multiplicity for that ideal j, and which is same as multiplicity of ideal I because it's a minimal reduction. Okay, so perhaps here I went too fast for the students, so you can check. So this is roughly the line. So this equation tells you something. What is the relation between EHK and E? So if I take dimension of the ring to be 1, then of course this has to coincide now, it says. On the other hand, if I go to the higher power, the story is quite different. In fact, multiplicity is always greater than EHK. This is the theorem of Douglas-Hans. On the other hand, this EHK can come very close to this one. So EHK being minimal in various senses, will come back to this question again. So let's compare once again the property of E and EHK. I think you have seen this, some of it in previous talks. So this one says one of the main purpose of multiplicity was to look at the regularity of the ring. So it says if R is regular, if and only if E of R at I is 1. Okay. But the same story holds true for the EHK also. So EHK is 1 if and only if R is regular. So this does detect the singularity of the ring. Okay. So one thing I would like to say here, this was given by actually Watanabe Yoshida, this result. So R is unmixed is not superfluous because what happens, EHK and E both do not keep track of the lower dimensional component. So even if the ring has a embedded component, the answer might still be 1 and ring may have embedded component. So of course the ring is not regular. So same is for the EHK also. So this to be more precise, look at this formula of associativity. So what happens, you take the pair R and I. So I can assume I can go modulo all the components components which give the same dimension as the ring, and you get the multiplicity there, and multiply by, of course, length of R localized at P. It's a finite.
Vijaylaxmi, there is a question from Professor Watanabe.
Yeah. Are you assuming I equal the maximal ideal in 2?
Sorry, what?
So your characterization of regular, are you assuming you are writing EHK of Ri?
Yeah. Sorry. Yes. I'm sorry. This is maximal ideal, both are. Yeah, right.
Okay.
I mean, it doesn't make sense otherwise. Yeah, sure. Thank you.
Yeah.
So, yeah, so now, so this is maximal ideal as Watanabe has pointed out. So associativity formula tells me as far as I need to compute E or EHK, I need to only look at the irreducible components of the R which give the same dimension as the dimension of R. So these are, so, but this formula tells me another thing that this, in fact, I could have put my module here, and the same formula is E of Mi is multiplicity of R mod P and length of MP. So for all purposes, I can consider my ring to be domain. And other thing says if taking Noether normalization if possible, etc., I can always assume a ring is normal. So that way this formula is useful. Okay, so this is another useful thing. So if I take two ideals J contain in I, again I have to put this condition. So both give the same multiplicity if and only if they have the same integral closure. Of course, I had to put this condition because length, just having a length equal doesn't say anything about two ideals. On the other hand, the similar thing holds true for HK multiplicity. So here it's a characteristic P version. The tight closure of I should be same as tight closure of J. So I am not recalling the definition of tight closure, but I would say something, tight closure is something which lies between, if I take a tight closure of ideal I, so it is something between it lies between the ideal I and its integral closure. That's why the name is tight closure. So this is a very characteristic P invariant of the ring. So note that the multiplicity doesn't depend on characteristic R, but EHK may depend on the R. In fact, on P, in fact, in a very strong sense. Yeah. So what is happening? So let me recall two properties of Hilbert-Samuel multiplicity. So it says if I want to study the E of Ri, I can take a general hyperplane section X, and its multiplicity, which is a lower dimensional ring now, is same as the multiplicity of the original one. In fact, this is a part of the definition of one way of defining your Hilbert multiplicity. So this tells me also that means I can always realize Hilbert-Samuel multiplicity as a Hilbert-Samuel multiplicity of a one-dimensional ring, say, for example. Okay, so induction is possible here. Then that Hilbert-Samuel multiplicity also remains same in a flat family. In fact, flat family, so here I am being little imprecise. So you have a good family and you have set of varieties varying over that family. So you take, say, variety to be base variety to be a variety of finite type over a field or something like that. So in fact, Hilbert function remains same. So in particular, the leading coefficient, which is Hilbert-Samuel multiplicity, remains same in a flat family. Okay. But these two, now very soon we are going to see that both the criterias miserably fail when we go about computing HK multiplicity. So look at the very basic example. So you take a hypersurface. So here it is, take K, X, Y, Z, and take a homogeneous polynomial of that, and look at ring R mod F. So it's a ring of dimension 2. So I am claiming that Hilbert-Samuel multiplicity of this is same as degree of the polynomial. So it's very easy to check, because to check the the E of this ring, you need to check only the length of each graded component of this ring, but which can be computed by this short exact sequence. So this is you take R, multiply by F, and send it to R. So this is degree preserving. So you have to just nth degree, length of degree n is the number of monomials of n degree monomials of R minus n minus degree f monomials of this. So this will just give it a leading polynomial, leading coefficient of the whole calculation given by degree of f. So this is very easy here as far as usual multiplicity is there. Now so we are looking at an algebraically closed field of characteristic P, and this is ring R. If I take proj of R, it's the famous Fermat quantity. So this is a very good, nice curve to have. Now they have computed HK multiplicity of R is 3 plus 1 upon P square if P is in the congruence class of 3 mod 8 and is 3 if P is in the congruence class of 1 mod 8. So this one is saying that if EHK also, the EHK property also is valid under general hyperplane section like this one, then EHK of the ring will be EHK of a one-dimensional ring, but that's equal to always a usual multiplicity as we have seen before, and which is independent of the characteristic like this. So certainly the general hyperplane section formula doesn't work here. The second example is given by Monsky. So look at Z mod 3Z and take its algebraic closure of this one. So you have now ring R lambda parameterized by lambda, where lambda is in K minus 0. So in A1. So again, this is a dimension 2 ring given by degree 4 polynomial. And this d lambda is what is the degree. So lambda belongs to K. So lambda might be algebraic over Z mod 3Z. In that case, it will have a irreducible polynomial. Look at the degree of that irreducible polynomial, and that is a d lambda. If lambda is not algebraic over Z mod 3Z, then you take d lambda to be infinity. So this term will be 0. Now you'll have infinitely many d lambdas if this is your definition. So that means you have infinitely many EHKs in this. Okay. Now here I said it remains same in a flat family. So any family of this type, which is parameterized by a variety of finite type, can have a flattening stratification, which is a finite flattening stratification. So it should hold only, there should be only finitely many values of this EHK R lambda, which is not true. So this property also fails just in the dimension 2 itself. Are there any questions?
Not right now.
Okay. Am I going too fast? Something?
I would say you can slow down a little bit.
Okay.
Yeah.
So far we have just defined HK multiplicity of the ring, and we said that it doesn't depend. It seems to be difficult to compute, at least not using the standard techniques. These are the demonstration I have given so far. Okay. Okay. So as a result, we have this. If I take, say, two-dimensional local ring, still we don't know the answer. Okay. Suppose we take a three-dimensional ring, hypersurface ring. Even F is homogeneous, we still don't have any good answer for this. So these things are, at least this example, as I said, for as far as usual multiplicity is concerned, is right away you get the answer, but here it's still a mystery. Okay, so then why is it interesting? So this is because we think that it will reveal more about the characteristic P features of the ring. And so in fact it is so. So let me give in a quick way one example. So suppose this is EHK is just a number here associated with the pair R and I. You take a plane curve. So that means KXYZ modulo some equation. That's your ring, two-dimensional ring. So if you have such a ring, so proj of that thing is a curve, plane curve, and then it comes equipped with a syzygy bundle on the proj. Now, there's a notion of semi-stability for such a bundle, for any vector bundle. So if I take a vector bundle, it is semi-stable. I won't define it right now. So it may happen that it is semi-stable, but if I take its finite pullback, for example, Frobenius pullback, it may not remain so. And this is a problem the vector bundle people deal a lot. But on the other hand, if it is Frobenius pullback is semi-stable, then it will be semi-stable to begin with. It's thanks to the Harder-Nursimon uniqueness property. So here, if I have a syzygy bundle, and if you give me if you give me EHK and tell me, and suppose prime underlying prime is greater than say d square, where d is a degree of the curve, that kind of thing, then one can say at what stage the Frobenius pullback of the syzygy bundle will continue to be semi-stable, and exactly when it will fail, and how much it has failed, which is called the destabilizing degree of the vector bundle. So this one number gives a good indication of the behavior of the syzygy bundle. So EHK, though it's difficult to compute, so is if somebody gives you a vector bundle, it's harder to compute this a Harder-Nursimon filtration. So we are basically relating one hard problem to another, but you got a many interesting property of syzygy bundle due to this EHK. So these are very old literature. So one of the most striking feature of EHK I find is this conjecture of Watanabe Yoshida. So let us see what it says. So Watanabe Yoshida had proved that if I take a regular local ring, its EHK is 1, and so among all the classes of rings, of course, regular rings are the best, and they achieve the minimal EHK. And what they are saying, that if EHK is 1, it has to be the best ring. That's what they have proved in the earlier notion. So here what they're saying, suppose if I don't take a regular ring, I look at the next best possible class, which is quadric hypersurfaces. These are the after regular rings. So they will achieve the least multiplicity compared to other kind of rings which are not regular. So this is what EH says. So this is very this thing. So EHK of R at n, I take any unmixed non-regular local ring, it will be greater or equal to EHK of the quadric hypersurface. This thing I'll come later. And the other thing which is very striking, they said that if the equality holds here, then up to completion, this R is isomorphic to this one. So just a numerical invariant is deciding about the ring structure analytically. So this is a conjecture, and I'll come back to this. Is in entire form, I think it has been proved up to dimension less than or equal to 6, and then rings of various lower multiplicities, etc. So I'll come back to this later. And the other feature of this conjecture, part of this is that they are saying that any quadric hypersurface of characteristic P, so it has a characteristic free lower bound, which is 1 plus MD. So MDs are this Maclaurin coefficients of Maclaurin expansion occurring like that. Say, take the expansion of sec x plus 10x, and this is. So MD is actually, you can think as an integer mod d factorial. So these are.
There's a question.
Yeah.
So the formula second tangent is found by Monsky, not by us. So
which formula?
Second x plus tangent x formula you are writing.
Yeah.
So that is found by Monsky, not by us.
Okay.
Thank you. Yeah.
But I saw this formula in your paper, so.
It's not found by us, and perhaps we wrote about that in the paper. So.
Okay.
Yeah.
I understand. Yeah.
Thank you. Yeah.
So this is a conjecture of Watanabe Yoshida for non-regular rings. So as I said before that this invariant seems rather elusive, and this conjecture has been pretty old, I think 2005 or something, if I'm right. And so still there is no complete answer. So one way of looking at all these questions may be to find some other approach here. So this is what I'm introducing today is called function instead of a number. So this next topic is the definition of the function and its properties. So this function is defined, of course, for a narrower class of rings, what you call a standard graded rings, because and where ideal I is also standard graded, because I take the help of gradation of the ring to define this function. So now you'll fix throughout R and I, where R will be standard graded ring, and just an R0 also you assume further to be a perfect field. And I is also homogeneous ideal of finite co-length. And here also I'm using D is greater than or equal to 2. So D equal to 2, we have pretty satisfactory answer, so it's okay. Now, so remember that HK multiplicity was defined using a sequence of lengths. So here the same thing we'll do. We'll define this density function taking the sequence of functions. So what is the sequence? So you take Q equal to Pn. So the Fn Ri, you give, just take X going to length of R mod I Frobenius Q and take its XQ pieces, the closest integer to XQ, length of that graded piece. So this is of order Q to the power D minus 1, just a Hilbert-Samuel polynomial formula will tell you. So you go modulo 1 to the power Q D minus 1. So this becomes independent of Q over the time. So now X goes to this. This is your formula. So for example, if my X was M, M mod Q, then this would have taken the length of mth graded piece of this quotient ring. Remember, I was also graded, so this is a graded quotient ring. So it makes sense. Okay. So notice this, by definition, this is a step function. Okay. So of course I can consider replace this step function, which is not continuous, by a continuous function just by joining the endpoints of the steps. So that I can call it Gn. So this is a sequence of function Fn or a sequence of continuous function Gn. Remember, as Q grows bigger, the step functions have more and more steps. So, okay. So what you will do, define density function to be this, take the sequence Fn Ri at X and take the limit of this. Okay, so this is your definition. So perhaps you'll ask then, but wait a minute, is this, does it make sense? Does limit exist? So answer is yes, and that's the thing. The ring, the sequence Fn Ri, which I just defined here, it converges to this function, not only point-wise, but in fact, it converges uniformly there. And okay. So this is the main point of the theorem. Other statement of this theorem follow automatically, because if Fn Ri is uniformly convergent, so if I take an integration both the sides. So integration will commute with limit. So integral of FNRI is the length of this one, length of RIQ, which is your EHK. So that's why you get this formula. So, and I forgot to mention, each Fn actually is, though I have written it goes from 0 infinity to 0 infinity, it actually, it has a it has a compact support. So in fact, all FNRI have a common compact support, I should say, they lie. So as a result, your converging function is also compactly supported. And as I said, I can replace Fn by a continuous function, say Gn. So limit of Gn will also be Fri. So it's just telling me that this function, density function, is your compactly supported continuous function on the real line. And it always takes non-negative value, of course. So are there any questions for this one?
No, I don't see any questions.
Okay. So far in the game, what we are going to play, that we are replacing the invariant, which is a number, EHKRI, by a function, which is a real function. So why is it? So what is the property of these functions? So first of all, what we should call associative property actually is the density function for a module M and I. So this is actually, I could have defined it for a graded module. So this is what same thing works. So density function for a graded module M and I is nothing but you just look at the density function at all irreducible components of the ring and multiply by length of NP. So once again, it says that I can assume for various calculation that my ring is a domain. I can also assume my ring is a normalization, because normalization of finite module over the original. So that property, as you've seen before, that it does hold for usual multiplicity and HK multiplicity, but this one is not clear. So this is a new feature of the HK density function. So you take the Segre product of the ring R and S. Okay. So let me recall what is the Segre product of ring. So if I take graded ring R, graded ring S, so R check S is a graded ring whose nth component is the nth component of R tensor nth component of S. And it's called Segre product because if I take proj of R and proj of S, take their Segre product and take it's a homogeneous coordinate ring. So it's going to be this ring, the ring of homogeneous coordinate ring of the proj R and homogeneous coordinate ring of S. I'm assuming everything is standard graded now. And of course, both of them should be defined over the same field to make sense. So here I have two pairs, Ri and Sj, with the same base field. So question is, what is the density function for this pair, Segre product of R and S? So in fact, it's given in a very simple way. So this is you take the polynomial given by E0 usual multiplicity of the ring at maximal ideal raised to the power xt minus 1. So this is simply just a polynomial, not compactly supported, note that. So similarly for any ring I can define. So this one is very easy to check because multiplicity will be just a product of multiplicity of R and S. So this I know very well. So this minus this density function of the Segre product is the product of these things, like a Hilbert-Kunz density function minus density function, same for this. So this tells me many things. It tells me, for example, if my R was a two-dimensional ring, I know its density function very well. It's a piecewise linear polynomial. So if I take a Segre product of two such rings, so it will be piecewise degree 2 polynomial and so on. So I can keep on multiplying. So those things, that information about Segre product comes for free in terms of the original density function. Okay. Then now I can take the tensor product of the ring and ask the same question. So what is the density function for tensor product of rings? To make sense, I need to consider these ideals, I tensor S plus R tensor J. So I won't define the gradation here, I guess everyone knows. So this density function of this pair is given as a convolution function of the density function of these pairs, Fri star Fsj. So what is a convolution function of two functions? So you take any integrable function, Lebesgue integral function, for example. So the convolution function is given by, you take x, f of, so you can see the formula here, fy g x minus y. Since f and g are compactly supported, this is going to be a compactly supported function. It's not a problem. So one way of looking at this function is very nice. These are compactly supported functions, all of them. So they are integrable. So real valued functions. So I can take the Fourier transform. So Fourier transform of this function will be pointwise multiplication of Fourier transform this into Fourier transform this. So if you go to a image of Fourier transform, this is density function of tensor product is the product of the density function. That's what it's saying. So much for the various properties of the density functions. So how much time I have, Jugal?
You have 20 minutes.
Oh, okay. So perhaps I'm going to.
No, it is fine.
So I kept on saying that my HK density function is a compactly supported continuous function. So this definition, maximum support of the function, makes perfect sense. So you take after this, your function vanishes. So this point makes sense given a pair. On the other hand, there is a well-known notion called F threshold of an ideal J with respect to Y. So here I should put some condition to make this containment sensible. Since I'll be dealing both like J and I like M primary, so that's okay for me. So the F threshold of J with respect to I is, you just look at what is the maximum power of, I should say, is maximum ideal of J you can embed inside the Frobenius power of I, and go modulo Q. So this is called F threshold of J. So this is given by, introduced earlier by Mustada, Takagi, Watanabe, and then the limit actually indeed they took in the form of Sup and Lim, Inf, I think. And then Stefani and Betancourt and Perez, they said that limit actually does Sup and in 2 coincide. So this is the way I present here. Now, let me say some trivias about this invariant. You may be wondering, what is this now? So in the minimal model program, there is a notion of log canonical threshold of I at M. So this is can be realized in this way. You just take this is a characteristic zero version, of course. So you go reduction mod P, take an analytic spread or something, and you look at the F threshold of IP at M, then take the limit, and this coincides with this. So not always, but in certain cases, this line should have come later. But so we are looking for this equality. We expect that this should hold. So we are trying to find a characteristic P variant of log canonical threshold. So this Blickel, Mustada, and Smith, and Mustada, Takagi, and Watanabe, I think this is, you need to have R to be F finite also, I think. what they said, these thresholds of J will coincide with something called F jumping numbers of J, which I'm not defining here. So, and the thing nice thing about F jumping numbers of J, if I go reduction mod P, they coincide with jumping number of J in characteristic 0. So as I said, these are characteristic P invariant of characteristic 0 invariants. F jumping number versus jumping number. Similarly, there are test ideals versus multiplier ideals given by Hara Yoshida. So this, I won't get into that. But so if R is not, okay, so normal Gorenstein, then this is the result of Blickel, Karlschweg, Takagi, and Zhang, that F jumping number reduction mod P coincides with jumping number of J. So this is, so these invariants are relating that way. So why we are talking of them? So this is a theorem with Watanabe. He says if I take R, a domain, here R is a regular, my R is a graded domain, unlike the other done by other people, a standard graded domain. Then you have a notion of a density function and you have a notion of support of the density function alpha Ri. So this function is always alpha Ri is less than or equal to D, where D is the dimension of the ring. And if D is equal to the dimension of the ring, then your ring is regular. So this is characterizing the regularity of the ring. In the case your ring is standard graded domain. In fact, if this happens, then your density function is a symmetric function, actually. Okay, so the thing which is crucial to us today is the second part of the theorem.
There is a question.
Excuse me. So, again, the I should be maximal ideal.
Oh, I'm sorry. This is yeah. I mean, whenever I mention regularity, it has to be with respect to at a point. So this is really stupid. So is this, of course. Otherwise, if I take general I can take a power of maximal ideal. This number can go will grow much larger. So this is I is M here. Okay, but this I is just an M primary ideal in the second statement. So this one says if my ring is strongly F regular on the puncture spectrum. So I won't define what is this notion, but assume if it is regular, then it's just strongly F regular. So for example, if proj of a R is regular, smooth, then this will hold. In that case, your maximum support of the density function will coincide with the F threshold of M at I. And so I forgot to mention the open question. So the open question we had put that does it hold if we remove this condition? So, okay. So now I'll give two application of this notion of HK density function. So Mustafa, Takagi, and Watanabe had asked this question. You look at this fix an ideal J, look at all its thresholds. Does it have some finite accumulation points? Be discrete. So if you take R to be a regular, then this F thresholds is a discrete set. This is proved by Blickel, Musata, and Smith. So here the thing is, when R is regular, your thresholds coincide with F jumping numbers, and which are known to be discrete there. Or other more general context was later proved by Montenera and Bittencourt, is that if R is a direct sum of a regular ring, this will hold. But that again, the proof is that you realize F threshold as jumping numbers there. Okay. So here's the result. So this one says, in fact, there exists a two-dimensional normal graded Gorenstein, Q Gorenstein domain, where you'll have you'll have a threshold of M will have an accumulation point. So I'll quickly say some lines about this sketch the proof. So as I said before, you have whenever you have a graded ring, you can take its proch. So this is a reverse way argument going on. This is you suppose you have a curve here and take an ideal. This is a situation which is generated by 3 elements of same degree. So you can this M primary ideal. So this map is surjective. Okay. So take its kernel. So it's going to be locally free because these are 2 locally free. So this is a vector bundle. So you have this short exact sequence. Now, as I said, for projective curve cases, we know how the density function looks like in terms of this syzygy bundle, the slopes of this syzygy bundle. So in particular, I know what is going to be the support point, the last support point of that density function in terms of this one. And this is what we are using now. So alpha Ri is given by one of this is so okay. So this is a mu. This is you take S Frobenius pullback of this bundle Bi and take the minimum slope. So what is S now? You should ask. So this is where the stage where your the bundle ceases to be semi-stable. Till lower Frobenius iteration, it is semi-stable, and here it has destabilized. So it has a non-trivial Harden-Nursiman filtration, and this is the minimum slope. Go modulo p to the power S, and E is your usual multiplicity. So this is a fixed number. Okay. Okay. So this is the thing, we already have this information in hand. Now we want to manipulate this one. So we are looking for a bundle, that means Vi, where this degrees keep changing and this one remains under control. Then we'll have an accumulation point, right? So we look for the Gieseker's example where he is actually given any non-singular, any genus, you produce a genus greater than 1, non-singular projective curve and a vector bundle with varying strong HN filtration. So these are set of bundles. So the job was to put these bundles in a bounded family. So you construct a ring as a result, a ring R, and IN, these are IN ideal generated by degree 3 elements now, all of them. It's a family of ideals. This should be R, IN here. So these have accumulation points because due to this syzygy bundle, which I said just now. So here's these INs will have syzygy bundles of varying slope. So this will be varying as N changes. So that was the idea of the proof. Okay. So this is one application. Looking at the maximum support of the density function, you are relating that to threshold and you are getting the idea because already you know very well of the threshold, the density function in terms of the vector bundles in the curve case. So though in principle it's difficult to compute a threshold also, exactly the same reason as HK multiplicity. So here you get it for free. So okay, so now we come to the second one. So this is the last application. So now let me go back to the Watanabe-Yoshida conjecture. So as I mentioned, this conjecture was in 2 parts. First part has 2 parts. So this was saying, the second part was saying that there is a characteristic free lower bound on the quadratic hypersurfaces. So this is for P not equal to 2. So are there any questions?
Right now. No, there are no questions right now.
Okay. So now you have this quadric hypersurface. So if I put some condition on P, like a P greater than or equal to D minus 3, if D is the dimension of the curve, if D is odd, and if D is even, then put P to be greater than or equal to 2D minus 3. So these are condition on P. In that case, the second part of the first part of the conjecture of Watanabe-Yoshida does hold, which says that EHK of the quadric hypersurface is indeed bounded by this number 1 plus MD. Not only that, it's bounded above by this number 1 plus MD to 2D minus 3 upon P. Okay, so so this one, you may say that means this, if I take limit as P tends to infinity, it does have a limit. In fact, this was proved already by Gesell-Monsky, that if I take EHK of this quadric hypersurfaces, so as P goes to infinity, it has 1 plus MD. So there are, so what is happening? This is trying to say that this is the best lower bound you'll have in the class of non-regular rings. It's because you can always find some number closer to this number. So for D less than or equal to 6, it was proved, as I mentioned earlier, Aberbach and Ionescu and Watanabe-Yoshida. Then there was Selig, Bass, Dao, Hineke, and Zhang have given other kind of lower bounds also. Okay. So this is so far my knowledge of histories. So how do we go about this function? So we again take the help of a density function. You take the density, compute the density function. So I have written in code because I'm not able to compute the density function. So I would like to mention the two relevant results here. So remember that Knorer has given a classification of hypersurfaces which have a maximal Cohen-Macaulay indecomposable modules. So these are arithmetically Cohen-Macaulay bundles. This is a projective version of that I'm saying. So he said also that, okay, so if I take a projective variety and take ACM bundle, on the other hand, if I take a corresponding graded ring, so MCM models are graded version of ACM bundles, you can say. So this is just a graded version of this projective thing. So this is a famous theorem, periodicity theorem. So he says his thing is more general, not quadrics. So there are hypersurfaces, and he says if I have a convergent power series or complete power series and go modulo hypersurface. Now look at the class of indecomposable Cohen-Macaulay, maximal Cohen-Macaulay modules on that. And now consider another ring. Another ring as follows: you adjoin two variables, and in the hypersurface, you take like two variables of y and z. So like f plus y square plus z square. So this is new hypersurface, which is dimension 1 greater than the original one. So the class of such modules are isomorphic, like maximal Cohen-Macaulay modules there, and the new hypersurface have the same isomorphism class. So this is a very strong. This is called periodicity theorem, as if they repeat after thing. So now, very soon after that, bookwise Heisenberg Herzog have proved, studied the specific thing which is quadrics and classified all the indecomposable graded maximal Cohen-Macaulay modules over quadrics. So this involves a matrix factorization of Heisenberg introduced by Heisenberg earlier. So upshot of this, what they have proved, that if you take such a module, and if you take, how should I say this? So up to indecomposable Cohen-Macaulay module, the non-free modules are, there is only one class of module which we call a spinor bundle. Depending on even and odd, there are 1 or 2. If there are 2, if the dimension is odd, in that case, those two modules are in kind of mirror image of each other. So just take some of them. So I'm just calling that as each of them. So up to the class non-trivial, non-free maximal Cohen-Macaulay modules on the quadric, there is only one called spinor bundle. Now combining this, what we get is you have a structure sheaf on okay, so this is you have a quadric hypersurface. Take its proch, so that's a quadric. Okay, and take the very ample line bundle, natural line bundle coming from this embedding. This one, it sits inside PD. So so I take its nth Frobenius and direct image of this bundle. So this is ACM bundle. It's easy to check because I can, as far as cohomologies are concerned, same as OM. So this will factor as a direct sum of line bundles and the indecomposable graded maximal Cohen-Macaulay module, which is only one according to bookwise Heisenberg's law. So this is the philosophy which I'm talking is not given by me. It's given by the work of Achinger. So using this factorization, so look at, let me go over it again. So you have O, take its mth number, m twist, and take its nth Frobenius. It will classify as line bundles and a spinor bundle. So these are the ranks for that twist. So let me skip the sequence. So the Achinger has proved the length of the quadric hypersurface, if I go modulo Frobenius power and take its mth graded piece, is going to be the rank of nu m 0m. So that is, take the zero twist here, t equal to 0, here t equal to 0, their rank. So it's going to be like this. So if you look closely, in fact, he has just given a ready-made density formula here, looks like. And he says, I also know when exactly these numbers, ranks are not zero. So question is, which of them actually occur? So he knows exactly, you can define, he has explicit formula he has given when they are not zero. The thing what he has not given is how much they are. Means they are not zero, okay, but what are they? So that's not evident. So that's where the almost compute problem comes in. So you just take the cohomology function, I'm almost done, I think. So of this one and try to compute these ranks. So you notice I have put a restriction on my characteristic because this restriction on characteristic tells me I make sure that at the most only 2 twist of spinor bundles exist, others are 0. That's a thing I ensure. But I can't enlarge further P and make it even less, because if I do so, then I'll be able to compute all the pairs. And when I say I compute all the pairs, means I can compute as a characteristic free way. There's no characteristic involved, you can say. And in that, if I can compute that, that means my HK multiplicity is going to be characteristic free, and which is not the case as demonstrated by Watanabe Yoshida formula. So it also tells me there will be at least 2 spinor twisters will be available. So that HK formula gives me free that formula. So this one, so I compute the pair. So you are able to compute for all this m and p to the power n where this mpn doesn't belong to this range. So look at this, if p changes, this range is of a very small order. So on this range, I'm not able to compute, but this one has others outside this, it has a polynomial formula. So you have, so this is what happening. So this will look like a polynomial, your function in this range, but that's not the complete story. It tells me something more. If I analyze this pair, it tells me in the rest of the range, this function will be greater than this function. So I just integrate both of them. So this will be the HK multiplicity of this, and this will be the HK multiplicity of the limit, which is 1 plus MD by the formula of Monsky and Gessel. So that's it, I think. And these are the, I'm done. That's all.
Okay. Thank you, Vijaylaxmi, for your very interesting talk. We are open for questions now. You can unmute and ask questions.
Excuse me,
Yeah.
Yeah.
Atana.
Yeah.
So if you give a homogeneous ideal I, a fixed ring R, then there is a density function. So
If you give a homogeneous ideal,
yeah.
yeah.
So and how much the density function characterize that ideal? So there are many things to consider. So for example, so if there is inclusion of ideals, so perhaps the density function is different in good rings, and so compare multiplicity product or
So you up to tight closure.
Yeah. Yes,
Up
of
to tight
course.
closure.
Yeah.
So as I have been talking to you, yeah.
So I am talking very vague idea, but so can we do ideal theory by density function? So it's not so concrete question, but
So are you, Keisha, are you saying that if an ideal I is contained in J and they have same density function, do they have same tight closure?
yeah.
Yes, they have.
Yes.
They have same tight closure, provided I is contained in
Yeah.
J. Yeah.
But so the difference, so perhaps reflects some property of ideals. And yeah. So perhaps the density function tells some property of ideal.
Yeah.
So,
I have been, as we have been talking, like if I is contained in J up to tight closure, so if the first stage where the tight closure doesn't coincide,
yeah.
that's where the function will separate. In fact, exactly that.
Yeah.
That's so that's in a way very delicate function up to tight closure.
Yeah.
Yes. So it does keep track of those things. So
yeah.
So you get there's some result of I think Karen Smith about inclusion of tight closure for things. So that follows from this theory. It is true. So
yeah. So absolutely, we could develop new ideal theory.
Yes. Yes. I think there's I think it looks nice actually.
Yeah.
That was a question by you. In fact, we did make some progress, but after that we couldn't talk. I think it is. That is correct. And yeah.
Okay. Thank you for very nice talk.
Thanks.
Thank you.
Vijaylaxmi, I have a question regarding Watanabe-Yoshida conjecture. So that conjecture is predicting that for non-regular local rings of characteristic P, there may be a notion of minimal HK multiplicity. So, in characteristic 0, rational singularities have minimal multiplicity. So, and do you think that if you take non-regular F-rational ring, it may have minimal HK multiplicity?
So, minimal. When you say minimal, generally it for me, minimal, it means minimal in what category? As if I'm looking at the category of certain kind of rings, then in that category it is minimal or something. So you are saying if it is F rational ring, it's a minimal in for which set of rings?
No. For multiplicity, we have we have a lower bound on multiplicity that in a Cohen-Macaulay ring, if you take embedding dimension minus dimension plus 1, that's a lower bound on the multiplicity always.
Yes.
And so where it is equal, we say the ring has minimal multiplicity. And you take a rational singularity which is not regular, it has, of course, regular local rings also have minimal multiplicity, but rational singularities have minimal multiplicity. So I'm asking now the conjecture of Yoshida and Watanabe is talking about non-regular local rings.
Correct.
And then computing their HK multiplicity and gives some universal lower bound, which is independent of the characteristic.
Yes.
So, of course, it is not yet settled, the conjecture, as you said. But is it an effort to establish a notion of minimal multiplicity in the context of SK multiplicity?
I don't know, but this conjecture just now I said it is true for if P is greater than D minus 3. It is this one, just now I proved this one, in fact.
Yeah. So these quadric surfaces, I suppose they are all F rational.
Yeah, I guess. Yeah. Isolated singularity there. Yeah, smooth quadric. Yeah.
Yeah. So my question is, if you take a arbitrary F rational ring, will it satisfy the Yoshida-Watanabe conjecture?
You mean this one or this one?
The absolute lower bound, 1 plus MD.
No, they are saying, in fact, for all rings, as long as considered, which is not regular, this should hold. I mean, this bound.
But it is still a conjecture, right?
So this part.
So my question is this conjecture satisfied for F rational rings?
That actually I'm not aware of it actually. You should ask Watanabe that what this conjecture is. This one I can tell you. In fact, maybe this one. Yeah. First part is for class of complete intersection rings when R runs over class of. Is proved by Inescu and Shimamoto, but F rational, I don't know. So, that's what exactly. Thank you. The second one, I'm claiming that I'm proving it for large P. That was my application just now. So, but Verma, you are asking something else. You are saying that if you take a class of F rational rings.
Right.
So I don't know. Maybe Watanabe might be able to say.
So the conjecture considers any non-regular rings. Okay. So and perhaps this ring is the simplest of non-regular.
Yeah.
And so I don't know how much it is proved just now, but for not this type, so any non-regular ring is so more complicated, more singular than this usual code ring.
Yeah.
So the Hilbert-Kunz multiplicity should go up.
But perhaps, Verma, are you asking that if I take F rational?
Yeah, if you take F rational ring,
which are not quadric. Okay, so I don't know, but
F rational rings are Cohen-Macaulay. All good F rational rings are.
No, one like this is the best bound it will be is expected.
Right. So whether 1 plus MD is the absolute lower bound. So
no, not actually. It's a best bound because that's what the that limit function of Gessel-Monsky is saying. This is the best bound. That's what it's telling you. So, so you can't do better than this. But this conjecture was improved by Yoshida, this 4-author paper which I mentioned in actually this last talk which he gave in this seminar. It's saying that if you take the class of rings which are not quadric, then there will be better lower bound. Where is the, sorry, the term, where did I see it? In this paper, so that's what they are asserting now. That's also conjecture. So far one can only prove this.
Okay. Yeah, I have another question. If you take a local ring and calculate the Hilbert-Kunz multiplicity of maximal ideal, now we go to the associated graded ring.
So it's not equal. It's a greater than equal to one way. So
they don't coincide.
No. It's a great. Which way I forget. But I think it is again by Watanabe will know, Yoshida and Ito, something like. Two people had given the example. Otherwise, you could have converted everything in the graded ring contest. It's not equal. Yeah, we know that.
Okay, thank you very much.
Yeah. Okay, bye.
Any other questions? Yeah, Thomas. Can you say what you want to say, Thomas?
Oh no, that was it. Just thank you for the talk. I really enjoyed it.
Okay.
Thank you.